In this presentation on electromagnetic waves, we talk about what happens when an electromagnetic wave encounters a matter or a medium. So basically, when an electromagnetic wave in general, could be light, but it can be any type of electromagnetic wave, encounters matter, three things can happen. So the light or the electromagnetic wave can go straight through that material when it encounters the material. That's called transmission. It can bounce off of the material, that's reflection, or it can actually be absorbed, and that's called absorption. So although these all say light, it's really true of any electromagnetic wave. So light actually behaves like a particle sometimes, and that particle is called a photon. And so when light interacts with matter, it behaves like a particle or like an object itself. And so just like you can have two billiard balls collide with one another, light can behave like one of those billiard balls, and it can actually interact with matter. And what happens is that the light actually can push charges that make up all matter. So we know that matter is made up of um, atoms, and that those atoms contain protons and electrons, and the protons and the electrons have electrical charge. And so light can actually push the electrical charge that makes up all of matter. So we're going to talk about these three different ways that light, or again in general electromagnetic waves, how they can interact with matter. So first we could talk a little bit about transmission. And so with transmission, I'm going to focus on visible light, but really just keep in mind that this is actually true for all electromagnetic waves. So with visible light, it's actually transmitted that's similar to sound when it enters a medium. So when light is incident on matter, so let's think about it in terms of glass, it can actually force some of the electrons in that particular piece of glass to vibrate, similar to tuning forks. When we had two tuning forks, if you strike one tuning fork, it sends out an electromagnetic, I'm talking about light now, right? So I'm sorry, it sends out a pressure wave for sound, and that pressure wave can cause another tuning fork further away to actually vibrate. So in a similar way, we can have light that interacts with the atoms that make up the matter, and it can cause the electrons to actually start to vibrate. And so energy is momentarily absorbed by the particular piece of matter. In this case, let's talk about glass. And it causes vibrations of the electrons in the glass. And then those vibrating electrons can either emit another photon, they can emit energy, or they could transfer the energy and absorb some of that energy as heat. Because there's this interaction between the light and the atoms that make up the material, there's actually a time delay between the absorption and re-emission of this energy of these vibrating electrons, and it causes the light to slow down as it travels through this particular material. So during transmission through a material, the speed of light is actually going to be less than what it would be in a vacuum. So we know that all electromagnetic waves travel at the same speed in a vacuum, but what happens is that when light encounters a medium and travels through that medium, it's going to slow down due to the fact that it's interacting with the atoms that make up that material and causing sort of this absorption and re-emission of photons. So during transmission, only the electrons that make up the atoms move, and the light doesn't actually lose any energy, it just slows down. Once it exits the medium again, it goes back to traveling at the speed that it had in a vacuum. So it's slower in the medium, but goes back to normal after it exits the medium. So here's a picture of that's representing the propagation of light through a material. So the green arrow here represents the photon or the light. And so when it travels in a vacuum, it just goes straight through and it's not interacting. But when it interacts with matter, it interacts with the electrons, causes them to vibrate, sends out another photon, causes it to vibrate, sends out another photon, and it eventually passes through, but it slows down during that process. Some matter or mediums are tuned to a particular frequency of the electromagnetic spectrum and allow waves to pass through the medium while stopping others from passing through. So depending on what a material is, it might allow some of the electromagnetic spectrum to pass through, and it might absorb some of the other electromagnetic waves in the spectrum. When absorption occurs, the nuclei also move. So not only the electrons here, which are vibrating and emitting photons, but the nucleus itself can actually move. It steals away energy from the light, and the substance can actually heat up because it's giving some of that energy that it was carrying to the atoms that make up the material. Some electromagnetic waves may not pass through, and it may just all be absorbed. And so let's look at some examples of that. So a material is considered to be transparent or opaque depending on the type of electromagnetic wave that's incident on the surface. So for example, a particular material, like a piece of glass here, may be transparent, meaning it allows transmission of some electromagnetic waves. So it would be transparent for a certain type of electromagnetic wave, but it would be considered opaque, meaning it does not allow those electromagnetic waves to pass through for a different range. So it turns out that for glass in particular, electrons in glass have a natural frequency that's in the ultraviolet range. So the glass is kind of tuned to the ultraviolet region. So when ultraviolet light is incident on glass, it causes resonance or large vibrations of the atoms and that collide with the light, essentially, and it produces heat. So when ultraviolet light strikes the glass, it actually does not pass through the glass because the glass is kind of tuned to that ultraviolet light, and it causes the glass to heat up. So glass would be considered opaque, meaning it does not allow transmission of ultraviolet light. On the other hand, visible light passes directly through the glass, and so glass is transparent for visible light. It's also opaque. Glass is also opaque for infrared light, so it does block that as well. So when we're thinking about electromagnetic waves and we're thinking about materials, we have to consider the fact that a particular material might allow some electromagnetic waves to pass through or be transmitted, and for those materials for those particular electromagnetic waves, the material is considered transparent, while all the rest that can't pass through, that particular material would be considered opaque for those electromagnetic waves. So for transparent materials, when there is transmission, the speed of light actually can change when it passes through, right? So in general, light will slow down when it passes through a medium. So now I'm kind of going back and talking more about visible light here, but it's actually true for all electromagnetic waves. So we know that in a vacuum, the speed of light is a constant, and it's about 300 million meters per second. It turns out that our atmosphere is basically very close to a vacuum. It's slightly less in terms of how visible light travels and electromagnetic waves, but visible light in particular travels through our atmosphere at about the same speed, 3 times 10 to the 8 meters per second. So it's a little bit less, but we round it off and we just say it's the same as a vacuum. When visible light travels through water, its speed is only about 75% what it is in a vacuum, so 0.75 times the speed of light in a vacuum. So it's about 3/4 what the speed of light is in a vacuum. When light travels through glass, and it depends on the type of glass, it travels at about 67% the speed in a vacuum, and it does depend on the material. And then just to give another reference, light can actually travel through diamond, and it really slows down in diamond. It's only traveling at about 41% what it would be in a vacuum. So the speed of light as it travels through a particular material is going to depend on what that material is. It's going to depend on the atoms that make up that material. And we can actually measure this speed, and we're going to eventually talk about how we can do that. In general, the speed of light in a material is still going to be calculated based on the frequency and the wavelength. So even though it slows down, the wave speed is still the formula for the speed of wave is still the same. So it still depends on frequency and wavelength. So if the speed has gotten smaller, so this value is smaller when light travels through a medium, then either the frequency and the wavelength has to also change, or maybe they both change. So the question is, what changes when light enters a material? The frequency, the wavelength, or both? And it turns out the wavelength is what changes. The frequency does not change. So whatever the frequency of light was before it entered the medium, it's the same when it's inside the medium, but the wavelength has decreased when it enters the medium. So the frequency of the light causes the vibrations of the electrons, and so since there was already a particular frequency of the electromagnetic wave, it's that frequency that's causing those electrons to vibrate, and they're going to vibrate at the same frequency. So the frequency is going to stay the same. So when you have absorption of light for opaque materials, when you have absorption of light without re-emission, the material is going to become slightly warmer due to that absorption because electromagnetic waves carry energy. So some examples would be metals are actually opaque to visible light. When the light shines on them, it forces the free electrons into vibration. They can actually emit their own light waves as reflections, but they can also absorb some of that light. And so if you've ever touched, if you're in your car and it's a really sunny day, you go out and you touch one of the shinier parts on your car, it'll be very warm, and that's due to the absorption of the visible light and also other electromagnetic waves. So it turns out that the Earth's atmosphere, and this is important here, is transparent to some ultraviolet light, this is what causes a sunburn if we're out on a sunny day. All visible light is transmitted through our atmosphere, and some infrared. But the Earth's atmosphere is opaque, meaning that it's going to absorb those electromagnetic waves in the high frequency range. So high frequencies of ultraviolet light, which can cause really severe sunburns. The Earth's atmosphere is actually opaque to those. So anything in the high frequency range, the Earth's atmosphere is actually opaque to those. So if we were bombarded, the Earth was bombarded by gamma rays, we actually are bombarded by gamma rays out in the vacuum of space at times. And those particular high frequency waves are not able to travel through the Earth's atmosphere, which is great. That protects us from receiving too much energy. But it is those high frequency electromagnetic waves that can cause damage, right? That can cause the sunburn, that can actually melt tar on roofs and roads and things like that. But it's really important that the Earth's atmosphere is only transparent to some of the range of electromagnetic waves, because there are a whole variety of electromagnetic waves out there that do bombard the Earth all the time. So sometimes we can actually have transmission of only a particular color of visible light through a piece of glass. And so what happens here is, suppose that we had a piece of blue glass. The reason that the glass appears blue is basically because it's made from a particular pigment, but in general, if we had this piece of blue light and we were to shine sunlight on it, and sunlight is made up of white light, which is a combination of all of the different colors, it turns out that only the blue light is transmitted through for that colored glass, and all of the other colors are absorbed. So that's why the glass appears to be blue to us, because we see that blue light coming through while all the others are absorbed. So this particular piece of glass would be opaque for all colors except blue, which can be transmitted. And the colored glass will actually warm up because of the absorption of those other colors. There's a PhET simulation that kind of allows you to play with that a little bit. We're not going to do that today.